So this is a question from Synchronous Machines resistance test. Now this is a question, interesting question, and I can see how you are approaching it. So let's break it up. Resistance testing is being done. So Wye construction, line to line, we get 2RA. Okay, I'm going to show that in a little bit. But like if you're doing it like this, right? So if you have an impedance, a piece of resistance over here, a piece of resistance here, these are the two terminals sticking out, right? And then you have your test, a voltage source, and you're measuring the V over I, and that basically translates into resistance. Then as you guys can see for a closed loop circuit, then this is going to be engaged, right? So that's a line-to-line resistance for the Y. But couldn't you divide the tester's outcome by 2 and get approximately the RA per phase? Okay. So let's look at that. Okay. And when you are doing this for delta, you are a little bit confused as to, you're considering these as parallel. So you're getting a little bit of a parallel arrangement. Test would give you 0.667 RA. Okay. So the way that you're looking at it is that, okay, I have these two terminals sticking out, RA is in between. So does it not become RA in parallel with the 2RA? Okay. So my take on this, if you look at it systematically, is that when we have a Wye connection, each line-to-line measurement includes two phase resistances in series. Okay. There are two phase resistances in series. If RA is a resistance of one phase winding, line to line is 2. So you are correct. We simply divided by 2. And I think I was pretty explicit about that in the lecture, right? So this piece is taken care of, Chris, right? This is divided by 2, right? When measuring the resistance in a delta from line to line, you are measuring across one single phase winding directly. Hence, the resistance measured will be RA naught 2 by 3. Okay, why is that the case? So you have a delta setup, right? The voltage is being applied directly on one of the phases. Okay, because this delta, so when we are testing, we are actually physically testing just one phase, because that phase is directly accessible. Okay, does it make sense? So in delta, what you do when you create a delta network, Chris, right? So you take one phase, right? You create a closed loop with the other phase, and then create a closed loop with the third phase. And that's how you create a delta, right? But this delta is comprised of three phases right now. When I'm carrying out this test on a delta, I am just testing one of the phases. Okay? Across one single phase winding directly. Knowing very well that when I actually come up with an equivalent phase circuit, right, for delta, remember that the line voltage, we just consider that as the phase voltage. Okay. So this is basically a single phase that will then be combined with two other phases in order to form a delta. But while I'm testing it, I'm testing this as a single phase. Does it make sense? Okay. So interesting question. And yeah, that's one of the key differences between delta and Wye. While we are at it, let us just come up with a quick scenario that, and this is something I hammered multiple times in the program. If I give you a line-to-line voltage, let's say 600 volt VRMS, I just call it VLL equal to 600 volt VRMS, okay? And then I ask you to figure out E naught, okay? And this is a synchronous generator, all right? Let's call it a synchronous generator. For a Y network, for a delta network. Now, sort of an extension of the same concept, when I'm dealing with a Y connection, do I have to, first of all, what is the equation? E naught is equal to what for a synchronous generator? Can you guys give me the equation for E naught? E naught is equal to the sum of the terminal voltage plus IA into RA plus JXS. Correct? Is that right? For a synchronous generator. Correct? So the line-to-line voltage of a synchronous generator, this is equal to what? E naught or V terminal? In the reference handbook, I think they call it E. V terminal, correct? Now here's the question for you guys. If I'm using a Y configuration for my synchronous generator, do I incorporate this V line to line as it is directly, or do I have to do something about it? Divide by root 3. Why? Because the voltage that is given to me is actually between these two terminals. Okay? It is between these two terminals, and that's a line-to-line voltage. And if I were to use this generator in a delta configuration and I've given you line-to-line voltage, will I still need to divide by square root 3? Or can I use this 600 volt as it is? I can use it as it is. Why? Because this voltage is appearing across the two terminals, and between the two terminals, I have a phase. All the equivalent circuits that we've discussed in the entire program, whether you're talking about a transformer, whether you're talking about an induction motor, whether you're talking about synchronous motor, synchronous generator, even when we're dealing with transmission lines, they are all on a per phase basis. So with the delta, you're already getting a per phase. Does it make sense? So only a single phase is engaged, and you can extrapolate that to this as well. Okay. While we are at it, what was the other interesting thing about this terminal voltage? Why is it super critical, super important? This serves as what? The terminal voltage always serves as a reference. Exactly. And what does that mean, guys? Reference means that when we are dealing with phasors, and again, as I mentioned to you multiple times in the program, whenever you are dealing with these equations, these are phasor quantities, guys. Angle is supposed to be, angle is needs to be taken care of. And the terminal voltage acting as a reference means that this is going to be 0 degrees. Okay. So great question, Chris. And I included it because it gives us an opportunity to review some of these fundamentals and be very methodical about it. As long as you approach these concepts from first principles, I can guarantee you that you're going to be fine. But as soon as you start operating in the gray area, in a wishy-washy territory, right, and are just going through the motions unconsciously, working through these, right, and just punching some numbers, you're asking for trouble. Okay? And that's the reason why synchronous machines and induction machines are so complicated, because they don't build on any one concept. I mean, there's not a single concept. So over here, if you take a step back, right, and look at the question that you asked, right, and the knowledge pieces that we had to deploy in order to effectively answer this question, there are plenty. Delta Y configuration, differences between them, phasor diagram, okay, your three-phase square root 3, 30 degrees, reference voltages, right? Understanding the equivalent circuit of the synchronous machine as to why this equation is the way it is. Because if this was switched to a motor, there are going to be changes in this equation, and that will have implications. Okay. So there are at least three to four fundamental concepts at play in order for you to properly answer this question. Okay. I hope you found this helpful. All right. Along the same line of thoughts, this is another question. So again, a very good student of mine asked this question. He's not on the call right now. The question is, for this problem, I understand your solution. What confused me a bit is how the handbook defines E naught and E. First of all, I don't control or can influence how they define what, right? They do not define them as phase voltages. No, they define them as line to neutral internally induced stator voltages and line to neutral terminal voltages. You see the voltage given in the problem statement, as always, is the line voltage. So something that we've already discussed, right? I get that it's delta connected, but like the case of transmission line and other parameters, just because it's a delta connected doesn't mean it's a there isn't a hidden neutral, and therefore that line to line voltage is always divided by square root 3 when doing the analysis. Okay, so the student's concern is that we have a delta system over here, right? And he's trying to figure out that what's the deal with the E naught and E. Okay, so he is looking at it from the standpoint of converting this delta into an equivalent Y. So he's not saying that these are phase voltages, right? So what is confusing him, and again, he's a very good student, so obviously the question has a lot of weightage, right? I mean, it's not a straightforward question because we know that the line quantity is equal to phase quantity in delta. And that's why, since we say that, okay, my explanation was that all the equivalent circuits on a per phase basis, right? So that's why we can take the delta voltage as a phase voltage. But he is actually digging in a little bit deeper, and he's saying that the way the E and E naught are described, they're line to neutral terminal voltage, line to neutral internally induced stator voltage. So he is feeling the temptation, getting the temptation to actually divide into square root 3 and do a delta Y conversion. Are you guys following what he's saying? Right? So here was my response. My response was pretty simple, right? Per phase equivalent system is constructed by V phase, okay, line to line divided by square root 3. So for obvious reasons, we need to have a per phase. Again, as I said, I cannot control how the reference handbook defines what they define, the variables that they use. I have no influence over that, right? The way I would like you guys to approach equivalent circuits is that remember that they are built always on the basis of single phase, on a per phase basis. Okay, I can see why he got dragged down into line to neutral, because that line to neutral sort of primes you, makes you think that, okay, I need to somehow extract, even if it's a virtual neutral that we've talked about in delta, by converting it into a Y. Now, if you stick with the terminology that the equivalent circuits are on a per phase basis, then the per phase equivalent system, when we are dealing with the delta, the line voltage is equal to the phase voltage, and we are going to consider that as our square 0 degrees, right? In both cases, terminal voltage is used as a reference. You guys see this? All right. So he's not 100% incorrect, but his assumption is that whatever is written in the reference handbook is set in stone. The way I am answering this question is that, okay, let them define it as such, right? You look at a few other textbooks, high quality textbooks related to power systems, right? They don't even use this terminology. They just call it per phase equivalent system, per phase circuit. And that's what I feel more comfortable using, because that is more consistent with how these formulas are developed. And if you want to learn more about preparation of FE Electrical and Computer exam and the P-Power exam, then check out these playlists over here. Thanks for watching, and I'll see you soon in the next video.